Let's say you have a population of 1 diddyblud and it doubles every year. It goes from 1 to 2 to 4 and so on. The function representing this growth would be an exponential function, 2 to the x. If I were to ask you, what is the growth rate of diddybluds for year 3, you would likely say it's 8, since the population increased by 8 in the following year. That could be right for the average rate of change from year 3 to 4, but I'm asking for the exact growth rate at time equals 3 years, or the instantaneous rate of change. How would we go about this? To do this, we need a way to define exponentials. We'll work with a generalized exponential a to the x. What we need to realize is that no matter what value of a you use, even if it's below 1, they are all stretched versions of each other. I mean horizontally stretched, not vertically. It's hard to notice that, but this animation is trying its best. What's also important is that every exponential goes through the point 0, 1. This is because anything to the 0 is 1, besides 0. How we will define exponentials is based on their slope at this point, which will help to show the horizontal stretch. It should make sense that we can define an entire exponential from one piece of information, since there's only one unknown, a. As we change a, the slope scales accordingly, and you can somewhat intuitively see that exponentials are indeed the same shapes but just stretch. Now, the most natural slope would be the slope of 1. You can assume it to be between 2 and 3 just from a little bit of trial and error. This special value, however, is exactly what e is, the exponential that gives the slope of 1 at x equals 0. Once again, we choose to define it using x equals 0 as all exponentials go through the point 0, 1. E just has the special property that its slope is exactly 1, the most natural slope, at x equals 0. If we want to differentiate any exponential in the form b to the x, we need to utilize a chain rule. First, we write it in terms of e by substituting e to the natural log b for b. This is because logarithms are the inverse of exponentials. Specifically, b to the log base b of a is a. Natural log is just another way to say log base of e. Anyway, utilizing exponent laws, we bring down the x and move it to the exponent with natural log b. This is where the chain rule comes in. We have a composition of functions here, the outside being e to the g and the inside being natural log b times x. We differentiate each of the functions individually first. E to the g becomes e to the g, as shown previously, and natural log b times x becomes natural log b through the power rule. To use the chain rule, we differentiate the outside and multiply it by the derivative of the inside. E to the x, the outside function, doesn't change when differentiated, so we just end up multiplying it by natural log b. Subbing back in e to the natural log b for b, we get the derivative. This is the generalized derivative for any exponential. Now you could figure out the growth rate of those diddybluds. Wait, diddyblud?